Jay, welcome to Talk Python to me.
Thanks for having me, Michael. It's a pleasure to be here.
It's a pleasure to have you. Congratulations.
Thanks. And of course, I would be remiss if I didn't, totally qualify this any congrats have to be accepted on behalf of hundreds of people at the NIF, at the laboratory, and laboratories and industry around, and indeed extending back 6 decades of research that went into this. And so, my part is insignificant, but not negligible.
I'm having a couple of my mental models broken recently. For me, fusion has always been one of those things that's always 30 years out. It's like,
Indeed.
we know it's possible, but it's just we're really barely scratching the surface. And the other mental model is AI is always 30 years out as well. And this year of ChatGPT and Stable Diffusion and all those things. And
things are changing.
Yeah, and this huge breakthrough that you all had, I'm sure there's still work to be done. You're not there yet, right? We're not all driving around with little tiny, water powered cars and stuff, but it shows that it's possible, right? And that it's a massive deal.
Yeah, no, you're absolutely right. There are a couple of big changes here in just the last months, even, right? So I'm still kind of processing both of those, actually. So yeah, it's going to be an interesting world. I think, as far as ignition, it is still a long path forward towards utilization.
It sure is. But
talk about that.
Yeah, we will. But it's so exciting because with renewables, that's great, but there's always the cost to that in terms of like, well, just think solar panels, like the mountains of e-waste of those things as they deteriorate over time, or just getting them all produced. But I think this is different, and I'm super excited to be diving into it with you. And I'm also really interested to hear how Python played an interesting role in it.
Yeah. I think that's kind of a fun story, and so I'm happy to have a chance to share it.
Yeah, and you've been central to it, which is it's fantastic. Now, before we get into all that, let's get into your story. How'd you get into, I guess, physics as well as Python?
Yeah. So I was, always wanted to be a scientist growing up. As a little kid, it was always space and dinosaurs and space and all. And that's how it sort of started. And then I remember it's actually just about this time, about 40 years ago or so. My dad brought home a Commodore 64, and so this would have been the after Christmas buzz of learning BASIC and stuff. My sister and I, and so that really started my computational journey. And then fast forwarding to, I got a degree in physics from Montana State University, did a cosmology with Bill Hiscock there, and then moved to California, took some time off. I worked at Chevron in the geophysics staff for a couple of years, met my wife there, worked at NASA Ames Research Center in Mountain View for a year. Then I decided to go back to school, which is what I always wanted to do. I looked around. I didn't really want to move very much. I was in the East Bay and in the San Francisco Bay Area.
It's nice there.
It is
and
nice
probably
there.
You have a family as well, right? Which makes it that it can also always be a tricky balance.
Yeah, exactly. That's always a constraint. And ultimately, it's a fairly stupid reason to make decisions. But it actually worked out very well because it made me look around. And it turned out there was this amazing graduate program at this place called Lawrence Livermore National Laboratory, run through the UC Davis, University of California, Davis, called the Department of Applied Science. And so I ended up going there for 5 years for a PhD and studied gamma ray bursts, the largest explosions in the universe. From across the universe, they send their high energy radiation from these giant relativistic mysterious explosions. It's very exciting. And I worked on modeling, doing a numerical modeling of neutron stars in their last few orbits and few milliseconds before they coalesce, as a defunct model for gamma ray bursts at the time. But it was a great experience programming in C++ and doing general relativity and such. And then I did a postdoc after that, and I got involved with another code at the lab that's actually people who are interested in numerical astrophysics might look into. It's called Cosmos with Peter Aninos and Chris Frigil at College of Charleston. Again, C++, doing more gamma ray burst research and such, and that's what I did until about 20 years ago when I took a job at Ignition with the ICF campaign, the Inertial Confinement Fusion campaign, and that's where I've basically been ever since. Then things sort of switched gears. I basically I still worked with Cosmos for a few years part-time, but really I kind of retired my compiled efforts and went more towards the interpreted world and got more involved in that, because then in ICF, the whole point was NIF was being built. It was still a hole in the ground at the time. And, but there are these big multi-physics codes. That's what we use at the lab to kind of research our ideas, to run them in simulation, see what they'll do. And we use interpreted languages to interface with those, either to run the code to help steer it, if you will, but also to post-process. And so I got really involved with a few languages, and Python didn't actually come to the fore at first. I was introduced to Python a little bit in the 90s. I wrote a little cron job that went to the Weather Service and put a weather map in my background every hour, which I thought was pretty nifty. And so I saw that it had potential. But one of the languages that I was first introduced to was Yorick, which was actually written by a physicist at Livermore, Dave Monroe, and so it's fairly extensively used at the lab, and it actually is sort of it has a causal connection to particularly the NumPy library in Python. I also actually got pretty involved in Perl at the time. Something about it I sort of appealed to me. I sort of liked its lexical structure. Larry Wall is a linguist and all. But it definitely, for the last 10 years or so, the weak couplings that are appealing about Python just kept coming back, and so I've since bitten down on that hook and drank the Kool-Aid pretty readily. And so for the last 10 years or so, it's been all Python all the time.
Nice.
Yeah.
Now you just got to tattoo the Python logo, and it's no going back.
Exactly. Yeah.
Got it.
You have one, right?
That's right. Oh, I keep my whole back.
Yeah, right.
One thing that stands out with that story, which is really interesting, I think it seems to me like there's quite a move in the sciences in general to move more towards open source and more towards sharing, in terms of, hey, if you use this library and we use that library, then maybe we can both have a better library type of sharing. Than there had traditionally been.
Absolutely, and that's something that I've been fortunate enough to kind of watch happen over the course of these years, and I think what we see, that it's nonlinear. It's just exploding. I think one of the appeals of Python has been PyPI and just this proliferation of packages, right? I mean, shout out your Python Bytes podcast. I find that to be quite fun and almost overwhelming, the new things that are coming out all the time, and you got to kind of keep up and pick and choose, but there's all sorts of new things, and the paradigm has shifted for me, and I think a lot of people, right, where, oh, I have this thing to do, I better start doing that, or crack a book or whatever. But no, it's like, let's find the package that already does that. And that's just a fundamental shift. And it's actually a lot of fun, I think. And you can contribute to
absolutely.
it as well.
Yeah, absolutely. I feel like when I went to school, I just took one or two, certainly one, maybe two computer science type classes. And it was all about algorithms and how can you evaluate, this bubble sort versus that, or this data structure versus that. And it seems a lot less, not that that's irrelevant, but it seems way more important now to, I can evaluate these libraries and pick this library, and it probably does something great inside, but I don't need to worry about it, right? It's more building with Lego blocks than it is, building with wiring kits. I don't know. Like, it's more big pieces that you just click together.
And kind of just to tie in, the very first inklings of what Chat GPT and Copilot and stuff can bring. I mean, I think Andre Karpathy made the comment that the new interpreted language is English, right? And it's almost getting to that point where we can just almost dictate what we want, which is sort of the next level of abstraction. And
Yeah.
I think that's just going to happen now, right?
Yeah, we're past the 30 years, I guess, and it's starting to
I
get
guess.
crazy. So, but I think this is really a positive move for the sciences in general, that so many of these libraries are available, and now you have thousands or millions of people working on it and using it, not just a single research lab.
Yeah, and it's nice to actually see, I think from my little vantage point, I'm not always aware of it, but the lab Livermore, for instance, and I think all the labs participate. They release a wealth of open source software as well. So it tends to be fairly focused on high performance computing. It has a niche, but it's definitely we're trying to give back and be part of that conversation.
Nice. So it's also a two-way street.
Yeah, definitely.
Well, let's start our conversation and our exploration here with some science, and then we'll get back down to the Python inside of it. Yeah. Let's talk about just all the stuff that's led up to fusion in general, and then the science and the attempts that have led up to this great breakthrough.
Yeah, so like I mentioned, actually, laser-induced fusion has been a research area for like 6 decades at the lab. I mean, when the first ideas were starting, when the first lasers were around, and the first people started thinking about that as a driver for fusion. And again, this concept of fusion is inertial confinement fusion. It's sort of based on the concept of taking some hydrogen isotopes. We tend to use deuterium and tritium. Those are the heavier versions of hydrogen because they have a higher cross section for fusion reacting, and we implode them. So yes, you have a diagram here that you're showing. So that we have a capsule, rather than that's distinct from magnetic fusion, which is sort of the other camp, where it's a little bit more like the fluorescent bulb model for fusion, where you're running plasma through a torus or some sort of a manifold like that, making it very hot but at low density, and maybe something a little more akin to the corona of the sun, say, and fusion will happen there in those schemes. And then here we're actually taking all of the fuel and putting it inside of one little capsule, and then we're compressing that capsule, getting it to very dense, as opposed to fusion or magnetic fusion, which is low density, very dense and hot conditions where fusion can transpire. And so that's it's actually sort of analogous, I think, to an internal combustion engine in that regard. So we're actually driving fusion. It happens and it blows itself apart.
Okay. Yeah. So the graphics that I had seen largely were those big torus-like structures. There's a name for that with a T?
Well, there's tokamaks and spheramax. Yeah, there's several
That's
concepts out there.
Right, that's the one. And so those, I think,
right.
is probably that's probably what a lot of people are familiar with. And this project is focused on aiming a bunch of lasers at a really small point and just really compressing it and heating it all at once, right?
Exactly. So, just to kind of give the outline, is just like you said. So the NIF is a big stadium-sized facility at the northeast corner of Lawrence Livermore National Laboratory, and in it is filled with 192 gigantic beams. Each one of them is basically one of the largest laser facilities in the world, and there are 192 of them, and they each basically work in concert to shine a pulse of just a few nanoseconds long. And this pulse goes down, and it's kind of, as the graphic you showed, they all are basically trying to converge at a point. But rather than just a point, what we put at the center of this convergence of all these 192 beams is a little tiny gold can. And so the can is about a centimeter high and maybe half a centimeter wide, and on the top and bottom, you put these two little holes, and the nomenclature, the laser entrance holes, LEHs. So it's rather amazing, these 192 beams of gigantic lasers, and when they're being amplified, they're actually several feet across, so the beams are spread out, they're huge, but they all get focused down to the point where they can all go through just a couple millimeter sized hole both at the top and the bottom of this gold can, and they shine into the can, and they shine on the inside wall of the can, and their goal is then to heat the can. Right, so you start with this laser light, and then you want to heat this can. And this can, we refer to it as a Hohlraum. That's a German word that translates roughly to hollow room, and that's just simply because it's something that holds the heat. And Hohlraums are actually everywhere in our life, right? Our ovens are a Hohlraum. Ovens heat up to temperatures of our infrared temperatures, right? We can sort of feel that heat. We can't see it, but we can feel it. If you get up, we heat these little Hohlraums up to actually X-ray temperatures, so that they're so hot they're beyond visual, they're beyond ultraviolet, but into the X-rays, and it's actually a fraction of the temperature at the center of the sun, in fact. And so we're actually bathing this little tiny gold can in this superheated X-ray environment, and then we inserted inside of that Hohlraum beforehand a hapless little capsule. And this capsule is about
It has
2
no idea what's
millimeters
coming.
across. Exactly. You kind of feel sorry for it sometimes if you anthropomorphize it a little bit. But and this capsule is made of, it's a very, very thin shell, just a couple hundred microns or 100 or so microns thick. And right now, these shots are being actually, they're used nanocrystalline diamond, so they're like pure carbon shells, and so they're very dense. And so it's kind of funny. We have a gold Hohlraum. The Hohlraum is made out of gold, and the capsule is made out of diamond, right? And so could you have picked more prosaic ingredients? But these are the ones that work. And so the point of this capsule is really just it acts like a rocket fuel. And so what happens is the laser energy is absorbed into that diamond, and it explodes. It just does pretty much exactly what you'd kind of think. It heats and explodes. And then, going back to your Newton's third law, right? So if you have an action, for every action, there's to be an equal and opposite reaction. If you have this little capsule exploding outward, right, in this bath of X-rays, whatever you put inside of that capsule has to go inward. And happily, we actually put in a little bit of deuterium and tritium, and we actually froze it into an ice layer around the inside of that capsule. So that becomes our payload. So the spherical rocket analogy is actually very apt. So you're having this fuel blowing outward and causing thrust that pushes the payload inward, and you try to compress it into a tiny little pellet, again trying to achieve very, very high densities, hundreds of grams per cubic centimeter, and tens of kilovolts. That's nomenclature. We can talk more about that. But to get to the point where you're actually at fusion conditions, and what you're looking for, and the goal, the reason why we're talking right now is the goal was always to achieve an ignition. So for a very long time, people have been demonstrated that you can get neutrons out of this. You can actually get a few of the billions of billions of hydrogen atoms in there to fuse. But what we're trying to do is get to the point where they bootstrap, where one fusion can cause another fusion or several more fusions, which will cause more fusions. And you get what's called an ignition, and it's ignition wave, where actually the fusions will cause more fusions, and they'll actually cause a burn propagating front to go from the tiny center of that little assembled piece of fuel, move outward, and actually propagate and burn fuel as it goes out. And that way you can actually that way you get a macroscopic amount of the fuel to burn, to convert to helium and release fusion energy, release neutrons. And that's what we've finally achieved. It's extremely difficult because basically everything has to work perfectly
in 192 lasers, and probably a chaotic dynamic reaction of some form of explosion and interaction there. It's not super easy to control, and there's some interesting Python planning some of those experiments and stuff. But it sounds to me that it's even though it's in a sense very much the opposite of fission, traditional nuclear reactions that
Mhm.
we already leverage. The way that it kind of propagates, and once you get it going, it sounds actually oddly similar.
Yeah, I mean, fission, the good thing about it is, or the nice thing about it is that it's passive, right? But it does operate on that same idea. If you put, fission products are really close together and one goes off, then it might cause others to go off and you can get that chain reaction. And exactly, that's, we're trying to get that to happen with fusion. But the thing is that, fusion, these particles are so light and they're all like charges, right? So they're all trying to push each other away. And as soon as you start putting heat into it, the product of fusion, the thing you wanted to get out of it, it immediately blows itself apart and turns itself off, unlike fission. And so that's really kind of always the trick.
That's the hard part. Yeah.
Yeah,
So
exactly.
you have to really carefully balance the lasers to keep the confinement happening and keep the pressure there until it takes off, right?
Right. Excuse me. So the lasers, I will give short shrift. Unfortunately, they're just amazing technological achievements, frankly. And I'm only just, I know a little bit about them. I know enough about them to simulate them, but they're amazing technological achievements that you can get all of these to run together. And what they do is actually they give this blast, right? They heat the whole room, and they actually heat it, not just like turn it to 450 like your oven. They actually heat it in these very precise stages that are timed all over the course of this few nanoseconds to actually, you're actually trying to ablate this rocket fuel in steps. You're not just trying to just blam. You're just actually, and doing that, you do that very precisely. So you're actually blowing a first step, and then you do another step, and then you actually hit it harder and really give it a good hard drive to really implode it. And all of that is happening by basically the lasers over the course of these few nanoseconds, just sort of pulsing in a sense, if you will, to heat this whole room, in these stages. So all of that has to be just perfect. It has to be very uniform, and then that ends up driving this capsule, and the capsule doesn't want to actually implode. And that's another big thing is it's unstable. Nature doesn't want to take nature. They always say nature hates a vacuum. Nature also hates when you take all the atoms in a room and try to move them into one corner, right? It doesn't let you do that easily, right? And that's basically kind of what we're trying to do. We're trying to take all of these fusion, these hydrogens, and put them all together into a tiny space. And kind of like you'd imagine, just trying to press a balloon together. We're trying to implode this capsule by a factor of 30 in linear scale, 20 to 30. And, if you tried to take a balloon and do that, right, you can imagine you push it in and it pops out where your fingers don't, where your fingers aren't. So you bring in a friend and you push together, and you're all pushing together. And pretty soon the balloon is finding tiny little places to squeeze out, but it's going to find them, right? And so you have to just basically iteratively, make everything as perfect as possible. And so the other hero of, I think, this achievement, not just the lasers have been just going through these rather miraculous increments beyond their original design specs, to the point where they're delivering more energy than they were originally promised, and with unprecedented smoothness and precision. But also the capsule and its smoothness and perfection is amazing. So like these capsules, if you just sort of think of out of roundness, they're about 200 nanometers, maybe out of a millimeter. And, the Earth is roughly, 20 kilometers out of round, out of 6,000. So these are, if you do those ratios, this is actually about 10 times rounder than the Earth.
Wow.
And, and it's just a tiny little, 2 millimeters across a capsule. Right. So they're very, very smooth. And that's something that's been progressing. And I would say those two achievements are kind of the things that had to be incrementally improved to the point where you're kind of just sort of you're trying to realize the ideal. Our codes are good at simulating ideals, and we do a lot of work to try to actually simulate the imperfections as well, right? And capture as many of those imperfections as possible. But we've always been able to sort of do the ideal and say, yeah, the ideal works, the whole spherical cow ideal, right?
It's
But
exactly
indeed,
pi around this ideal circle, and of course it's going to work like this, and there you go.
exactly. And it's like, oh, that works really well. And that's been the issue. And really what's happening is these large teams of experimentalists have been able to make the laser better and continue to and make these targets better, and they're actually getting closer and closer to ideals that even just a few years ago were like ridiculous. So it's really a testament to that hard work.
Yeah, really amazing. So what we're all learning is to collapse this balloon, you need 192 friends or 191 friends if you don't count yourself, right?
Right. Well, the fact that we're doing a can like this Holram is very important. We're not actually shining the lasers on the capsule. That's something that's called direct drive, and indeed that is a field of study that provides its own challenge, because indeed each laser is like a little fingertip trying to push on the capsule. This is so-called indirect drive because we're driving the capsule by the heating bath of the lasers. The lasers are heating this Holram, and that's driving the capsule. And it's more the shell that is playing the important role of doing the compression, and you need to provide just enough controlled and even heating to make it go. Right. Yeah. You want to make that, but you still need to make that heating as controlled and even as you can. And it's still not even enough really so there's been, you have to do a lot of work with, making sure that heating, where you put the beams, where the spots are, which are kind of like the elements in your oven, right? If you turn on the broil elements, you'll burn your toast, right? And so you have to know where to put those elements, where do those spots hit the inside of the Holram to heat as uniformly as possible.
Yeah, and people might be thinking, well, compressing something 30 times, it's not that crazy. We do that with air all the time. You look at combustion engines and other stuff, but you're also heating it
30 times linearly.
Yeah, but you're also heating it to near the temperature of the sun. It wants to get a lot bigger really quickly. It doesn't want to even stay where it is, right?
Absolutely, yes. You are heating it up to actually temperatures in excess of the center of the sun, and so yeah, and it doesn't want to be there.
It wants to get moving. All right, fantastic. Let's just talk one more science side thing, then we'll dive into the software side. So this is the first time this has been done, and it's a huge accomplishment. How do you all see this very quick and small reaction potentially turning into actual energy sources? Where do we go from here to do something productive with this?
Right. So it's important to note that the National Ignition Facility itself is a demonstration facility. It's a research facility. So it's not meant to become an energy facility. And indeed, there are other startups out there, and I think there are probably going to be more that are exploring ways to commoditize this. So it's kind of interesting to kind of think about the energy a little bit, if I can, so just to kind of add a scale to this, like a human eats about 2,000 calories of food a day, right? An adult, right? And those are actually kilocalories, nutritional calories. So that's 2 million calories, which is, 2 megacalories. And it turns out that a calorie it's kind of convenient is 4 joules, another scientific measure of energy that we use all the time. So that two kilocalories we eat every day is basically, 2 million calories, which is 8 megajoules, 8 million joules. So you just multiply by that 4. So 8 megajoules you eat every day, right? So this laser is producing 2 megajoules, sort of like your breakfast, right, of energy. So it's actually not an inachievable amount of energy, but it does it in just a few nanoseconds, right? And I don't know how to describe a nanosecond all that well, except to know that that the speed of light is a good measure, right? The speed of light. So at the speed of light, a light wave can go around the Earth 7.5 times in a second. but in a nanosecond, light only goes 30 centimeters, so about a foot.
Wow.
And so I think that gives you an idea of just how quick that is. And
It gives
so
you a sense
that's the
also
key.
of how, yeah, it gives you a sense of how insanely precise those lasers have to be because
Exactly. Yeah.
they've got that 30 centimeters, you know,
Right. The entire, yeah,
section to get.
that's the cosmic speed limit. No information can go faster than that. And so everything has to be within this really small envelope.
Okay.
It's quite amazing. And so, and then, the reason why we're talking about this particular achievement is that it actually yielded a little over 3 megajoules. So maybe, breakfast plus lunch in fusion yield. And again, that happened, instantaneously, effectively. That was released. So it's more about the release that makes it amazing. So, but the thing is that the energies aren't all that large at this point. And it occurred to me that, if you, so, well, if you think about, it's kind of interesting to think about, like, so going back to the food analogies, you eat 8 megajoules per day. A day is 24 hours times 60 minutes times 60 seconds. So 24 times 3,600, it's 80 or 90,000 seconds, right? So 8 megajoules divided by, say, 80,000 seconds, that works out to 100 joules per second, or 100 watts. So you as a human, burn 100 watts, right? Which is a very, we use that term all the time, right? So we're, and you can kind of imagine taking a mannequin and putting a 100-watt incandescent bulb inside, and it would kind of heat up to our skin temperatures. So, but we're, of course, we're going at a much higher wattage because we're doing it very quickly. But so you can actually sort of think of, like, a unit of measure that we often use in electricity and stuff is, sort of the kilowatt hour, right? 1,000 watts times an hour, which is, again, just 3,600. So if a kilowatt hour is just 3.6 megajoules, then, so 3,600 times 1,000 watts. So 3.6 megajoules is a kilowatt hour. And not to put you on the spot, Michael, but do you know how much you pay per kilowatt hour for your electricity in your home?
I think 17 cents.
Oh, that's awesome. I'm so depressed.
I'm pretty sure, as long as I have the units right, because
yeah, no, that's about right.
Since I have an electric car, I have little stuff that'll show me, like, here's how much you charge and how much it pays. Enter your price here to get your, like. So I'm pretty sure it's 17. It might have gone up just a tiny bit.
No, okay, yeah. So I pay about 25 off peak and like 45 cents per kilowatt hour on peak. And so I have an EV, and and I'm kind of aware of all that as well. But so again, this shot produced about a little over 3 megajoules when a kilowatt hour is 3.6, right? Which is, like, as you said, you can buy one for 17 cents. So I can pretty much say with certainty that this experiment cost more than 17 cents. Right.
Even
and
if
so
you
I think
scale
that
it up, somewhat, it's going to be more than 17 cents. Yeah.
So yeah, this one experiment for my one kilowatt hour I got out of, or a little less than a kilowatt hour I got out of it. Right. That's and never mind that there was a certain amount put in. I had to put 2 megajoules in, and there's inefficiencies as well. But so I think that just sort of outlines the challenge of scale, right? I mean, so, I have to make a capsule that's way cheaper than 17 cents to make money. I have to, probably I'll want to get more than a kilowatt hour per shot. I'll probably want 10 or 100 kilowatt hours per shot. And then I'm going to have a high rep rate, because ultimately, to power your home and my home and a town's home, you need lots of kilowatt hours. And so scaling it up is a challenge. And I think that's just sort of a nice way to illustrate, where you have to go to get there.
Yeah, you got to start somewhere, though. The first transistors, I'm sure, were expensive. The first
exactly
100 kilobytes of hard drive storage seemed just insane. If you told somebody, well, we're going to need a terabyte on everybody's computer, like, yeah, no, we can't do that. And here we are, just on an SD card, nothing. Yeah, so.
Exactly. But there's a lot to do. There's a lot of growth there that needs to happen.
It's early stage for sure.
Right.
Awesome. All right, well, let's talk about some of the software side. I know that you guys have over at the LLNL, Lawrence Livermore National Laboratory, you have a software portal. We have a bunch of different applications and things that you're sharing, which are really great.
Mm-hmm.
And so I know that you've got a lot of neat things happening on the software side. Your area has been largely around designing and simulating the experiments. And then once someone runs them to go, okay, I got some data. How'd that work? How do we adjust? So maybe
Yes.
talk to us about some of the software side of what you're doing there.
Yeah, right. Uh, so like we are saying, our kind of design cycle is that we have these quite impressive multi-physics codes that can simulate these experiments, right? That actually mock up the whole room and the capsule inside, and actually put fake lasers in and run how they would interact with the gold atoms, and actually run the entire simulation. Um, but usually don't want to just push the button and just have it come out. Usually you're asking questions about it. You're instrumenting it up, if you will. You're checking things. So you're kind of steering these simulations. And so one of the big facets of software that we've been working on for the last few years is to improve that steering in Python. We can talk a little bit more about that. And then, but then also we have, so then you get out your simulations result, right? You say, oh, well, this result did such and such, right? But now you want to actually compare it to data. And, so you have to go over to a web page or talk to somebody who ran an experiment on NIF and talk to them and get that data. And so that's another area that we've been working really hard on over the last 5 or 6 years. I've been to try to improve that ability so that basically we're kind of bringing all the parties together so that making the simulations easier to run, easier to work with, and also having the data and tools proximate to that so that we can all sit in one place and actually ask all the questions and get all the answers in that one spot. So I guess so historically, that's kind of been the design cycle, and it's been fairly organic, right? Where people will write tools that work for them to steer code or to do some post-processing, and then they'll share them with people. And, and then somebody else will share it and they'll tweak it, and it'll, and eventually somebody will quit asking just friends, and they'll put it in a directory somewhere and make it readable. Right. Mm-hmm. And so, that had been the way, we'd done business for a while. And we're trying to actually improve that. And so about 5 or 6 years ago, I was designing some experiments for the NIF, and I was running one of these tools that were sort of an organically grown thing, and I was trying to do something that was a little bit challenging for it and a little bit out of its strengths. And I basically kind of had an existential crisis. I just thought, I can't do this anymore. These tools aren't cutting it. The code underneath is great, but I'm just beating my head against the wall to talk to it and to get things out of it. And, you can really burn a lot of human time doing that, which is very expensive. And so I basically just stopped running those tools. Like, it was just, kind of like the old Office Space thing, where the guy post-hypnotic suggestion, right? I just thought,
I don't think I want to go to work today. Well, how are you gonna pay your bills? I don't think I want to do that either. Like, just kind of done, right? No.
It was kind of
mental model.
Right. It was kind of like that. I just felt like I can't do that anymore. And I think my time would be better spent trying to improve the model, improve the ecosystem. And again, so I am drinking the Python Kool-Aid all the time, learning more and more about the ecosystem, also learning just about, Git and continuous integration, just things that are out there that I've been entirely naive about myself. And realizing that, there's actually things to do. And in all fairness, of course, other people are thinking things like this as well. As per the page you've got up here, the lab has tons of people who are doing this stuff in spades. But in our little corner of ignition land, that wasn't happening as much as I wanted. And so I basically looked around, and I found a couple things that other people had just been starting. And one of them is basically a Python wrapper of one of our codes. We have one of our multi-physics codes. We call it Hydra. And the developer physicist Joe Koning did the hard work of actually installing Python in a Python interpreter into that, so it actually talks to this big multi-physics parallel code. And
interesting. So it's actually hosting the Python runtime, not the other way around, where Python is trying to wrap its C API.
Right. No, the code itself is running, and Python is just bolted on top of it. And so
Okay.
yeah. So the code is still in control. It's actually very challenging, and Joe did a great job of doing that after the fact. But now you have the ability to actually, to initialize the problem and tell its run state purely in Python. And he was starting to build an infrastructure to develop our problems, our ignition problems, these holorums and capsules and such. And I just jumped in on that. I thought this is what we have to do. It was a tremendous amount of effort to build that up to make it something that actually worked. But I think that it's actually one of the easier tools out there and most robust and user friendly tools we have now. And so that's sort of the one half of the puzzle is just making a Python interface, a purely Python interface to run these tools. And again, so this tool we call HyPy for the Hydra Python deck. And again, Joe Koning initiated it, and I've been really involved. And Chris Young has gotten involved since then, helping a lot. And so we basically just tried to build the entire ecosystem of how do you initialize the holorum and the capsule and the laser and all of those things, so that you can tell this Hydra code to run and give you some results, right? So that's been a big push that I've been championing and proselytizing on. The other half of it, and this kind of goes back to Dave Monroe and Yorick, like I was mentioning earlier. A lot of people use Yorick. It's a very, very useful tool for data analysis. It's an interactive tool with a very, very nice array syntax. Think of it kind of like interpreted C, if C was, if C syntax was just interpreted with a really nice array syntax built on. And so it's still quite widely used. But I think to Dave Monroe's credit, as he was nearing retirement a couple of years ago, he decided that Python was the way to go. He decided that the future was going with the leveraging what's out there and just going with Python. And he wanted to
pretty bold when you were the one. Sorry, that's pretty bold when you're the one who created your thing and you're like, you know what, I love my baby, but it's time to think beyond it.
Absolutely. I don't think he gets enough credit for that. I have immense respect for that, because I mean, I don't know if I would do that. There are a lot of people become very protective of their babies, right? But no, it's what's best, right? And so before the thing that's nice one of the nice things about Yorick is a lot like MATLAB or Mathematica. When you type Yorick and open a shell, it's everything you get is right there, right? It's a single environment, and like it or not, Python is a little more heterogeneous and diverse than that, right? And it's a feature and a bug. And so one of the things he wanted to do was to as sort of a parting gift to us is he created this tool called iDesign that is basically, at its core, it's a Python virtual environment that just pip installs all of the packages that we like to do. There's a lot of them that we've been building, to create this Python ecosystem that will then talk to this HyPy Hydra, simulation layer, and basically then everybody can just type Python and they'll get that environment. And
Excellent.
that by itself, that's not all that big a deal, but it does actually have a certain amount of nice features that we've been able to build it into our GitLab continuous integration environment. We've built an awful lot on it since he did retire, and so you can take snapshots of the environment state and some other things. So people have told us we need to open source that. I've sort of balked at it, but I think I've made the decision that we're going to. So iDesign will eventually be on that page you were showing earlier. So hopefully in a year or whatever, we're going to do that. But another key component, I think one of the things I get excited about, and it's one of the things that's exciting about Python in general, is the fact that, that you can have these it's an enabling technology, right? And so now that you have an iDesign environment, everybody can come into a uniform Python environment and everybody speaks the same languages, has the same tools at their disposal. Well, now you can actually build in tools to go grab data from the NIF databases, right? Where they're running shots and they're compiling all of this data. It's not always as easily accessible as you would like for maybe a non-expert in that particular diagnostic or whatever. And so what we've been doing is another big campaign, that a part of this iDesign ecosystem is that we've been building what's called a shot data pipeline. And again, this runs in the GitLab continuous integration environment. Every night we go off to a bunch of databases and just harvest a whole bunch of data, bring it in and rebuild this iDesign environment with physical data, again, the tools, and then the ability to actually run the code all in Python, right? All in one environment. And so this is kind of, I think go ahead.
Yeah, probably before, when people would run the experiments, I don't know what before is, maybe way far back, but when you get started, you're like, okay, I got to get the data here, and then we got to maybe process it and then convert it to this other form and then filter this down. And then finally we can get it so we can import it over here and process it. Right. And so you're talking about, well, what if you had a CI pipeline that could do a bunch of these sort of steps, right? Is that the idea?
Basically, so there are experimental physicists who know their diagnostics extremely well. And so they actually will take that raw data and distill it to something useful. We're really just doing the more prosaic step of going and getting it and bringing it so that it's proximate to the designer. And, and, that's one of those things. It's like, well, yeah, right. Just go get it. But it's a huge task, and it wastes an awful lot of designer time when you have to chase down data for shots. And so this is something that we're actually, well, it's not a lot of data really, but per shot you might only be dealing with, a few numbers, few scalars, right? And then it can go up to images, and it can go up to, you can ask for a lot of, you can get more detailed pictures, but even you might just be looking for just a few numbers. But the thing is, if you have to go ask for those few numbers every time, and it's not like it always has to happen. It just, there wasn't a process in place to just sort of try to, that was sort of the culture, right? When you want something, you just go ask somebody, right? And that's fine. But we've been trying to make the culture a little bit more like, let's provide it, and let's automatically create it. And I think that's been really an exciting, and this whole Python framework has been the enabling technology to allow that to happen. And we're just at the point now over the last year or so that, in fact, a lot of this stuff is still coming to fruition right now. You'd still consider it alpha and beta, but it's actually, it's finally coming together, which I think is really exciting. And that starts maybe kind of slowly changing the culture, right? Where people start expecting, hey, it's actually easy for me if I just put my data in a spot, and those shot data pipeline guys, we're going to just go and harvest it every night, and we'll just, I don't have to worry about it. I don't have to field emails.
Once the foundation of the automation is there and people start to realize they can trust it, then you start to get creative and put more things on there and leverage it more, and it just makes a lot of stuff take off.
It's PyPI, right? Writ small.
It is.
It is. And another part of that is that the design community, which again, I talked about how a lot of things, people will develop tools and then they'll just share them when asked, maybe put it in a directory somewhere. Well, now we have a place where you can actually have your own repository, and maybe a physicist isn't all that interested in learning what a Git repository is, but we can help with that, I mean, and it can become a place where you can have your tools and they're available and they're deployed, because we also have the issue that we have systems that are air gapped, right? And so we need to have this whole distribution mirrored over here with a physical pass off, right? And so we try to do that now regularly rather than just piecemeal. And hey, if you create a little tool or whatever it is, it's just everywhere all of a sudden, right? And that's really new, and I think that's again very empowering for for the designers who are creating these NIF experiments.
I think people who haven't experienced it, these organizations, these research labs and other similar places, they basically become software companies. At least they have a software team that is functioning really at a pretty high level in them. I worked at a research place that had 6 or 7 PhDs and a bunch of grad students, and me and another software developer, and we were writing software full time, and it kept getting better and better. And what actually the grad students would say to me is, if you keep doing this, we're going to be out of a job. All the software you're writing, this is what we do. And like, no, what you're going to do is you're going to do actual science and actually better stuff. And every time they'd be like, well, this was my job, and here it is a button now. And nobody was fired from that. They just did more interesting stuff and took on more ambitious projects. It's
Ding,
pretty
ding,
cool
ding. Exactly. And I've been accused of that before. Like, you're going to put us all out of a job. And it's like, no, your job is so much more interesting now. And my job is more interesting. I mean, I spend a lot of time developing now. I've kind of, made this my passion. And so I have a smaller fraction of my time doing designing experiments, not zero, but smaller. But I actually feel like it's much, much more efficient than it ever was. And
yeah,
so,
you might have a bigger
way,
impact though, even though it's less time.
Yeah, it's just a lot more. Yeah, exactly. It's just a lot more efficient, and it's fun to show younger people who are coming in how to do this, and that it doesn't have to kind of be sort of what I consider a painful cycle. I mean, maybe some people enjoy it. Yeah. So I like to say that I feel like I'm building the tools that I wish I had when I started. And I think I can, it's happening, and again, we have a really, I have a great team of folks that we're working with. I work with, computer scientists, Ryan Tran and Jimmy Smith help me build this stuff out. And it's just been, it's been really great.
Sounds fantastic. How many people are on the team?
So it's just a small, and a certain amount of it is just people who want to help. So it's just a few of us. Again, Joe Koning and Chris Young and Dave Strozzi and such. So and again, but then there are a lot of people who are starting to become contributors, and I think that's where the leverage starts. Sort of a stone soup thing.
Yeah. And on the NIF more broadly, how many people are involved?
NIF, hundreds. Jeremy on the call here might be able to give an actual number, but it's hundreds of scientists. And so, for scale, you have to keep in mind that the Lawrence Livermore Lab has thousands of scientists. So even though the NIF is a big program, it's actually fairly small as a part of the greater lab portfolio. And I guess I want to emphasize that I'm speaking kind of for the design corner, right? There's the experimental corner, the people who actually work with the hardware of the NIF and stuff, and we talk to them particularly vis-a-vis the shot data pipeline, but there are a lot of places that have their own architectures. You can see that with the open source page and stuff. So there's a tremendous amount, but I'm and a lot of those things are doing really great, their own great infrastructures. But this is really speaking towards the needs of the NIF ignition community.
Yeah. So you talked about the specific libraries that you are really focused on the work there, but I'm sure you used a bunch of standard Python libraries, packages that people are familiar with. Maybe give us a sense of some of the tools and things that were at play that you're taking advantage of.
Oh yeah, well, of course we're using all the NumPy, SciPy stuff. That's sort of a given. And we also in iDesign will bring, we have Plasma Pi and X-Ray DB and some of these, again, these really nice physical data packages that people have developed in the open source community that now we just sort of bring in so that it's always maintained for designers at your fingertips. certain number of us also do. Yeah, there you go. The page there you brought up.
Yeah,
Uh,
pip install Plasma Pi. What kind of install do you prefer?
there you go. Yeah, and you know, a lot of us, including myself, are getting involved in you know, machine learning as well. Of course, that's an important part of the an emerging, you know, technology people are excited to take advantage of. And so, like, you know, I install PyTorch into iDesign, and try to make sure that's, which is a bit of a challenge, right? Because we have a really large different architectures, you know, and taking advantage of their different GPUs. You have to, you know, it's not necessarily just a pip install. I might have to compile it, and so that there are challenges there. But we try to, you know, just make that available for the, you know, design community, which is cool. Because again, I mean, not to harp on the enabling technology thing, but you know, we can now, and you know, I do again as a research thing. I can import PyTorch into my HiPy, you know, that runs my big Hydra multi-physics simulation, and have it do inference on some part of the, you know, on part of the simulation, right? And maybe, you know, even offload part of that. And so there are other efforts at the lab as looking at those kinds of things as well. But again, I don't know how you would do that without these tools that we've been building, frankly, at least in our corner of the world.
Yeah, you got to keep building that foundation until everything is ready to click it together. Yeah,
exactly.
While it's fun to imagine what would happen if you asked ChatGPT to, you know, say, imagine ChatGPT, you had the most precise lasers in the world. How would you design a fusion experiment? I'm sure that's not going to result in much. Where do you actually see like real, you know, constructive AI applied to this, or machine learning? Do you have anything that you see on the radar there?
So yeah, no, that there are several things that are being that it's being applied to, and in fact there are, I think there, you know, maybe there can be, you can find some links here that there have been some there's a group that sort of predicted, there gave some confidence whether this shot was going to achieve ignition, right? Where they're trying to learn from the experience of past shots and try to get some idea of predicting whether how a future shot will perform. And so those are you know, new things that are happening. Sort of, I think the two sides of it are probably those kinds of high level things where you're trying to ask it, you know, big questions about, you know, what would happen if I do this. But there's the other level of kind of using it to offload some of the big numerical heavy lifting that we do all the time. So we run a lot of you know, these simulations run, you know, have massive calculations trying to, you know, do the physics of these lasers shining into these holograms and such, and some of those calculations could be learned by an inference engine and just maybe a simplified version provided over and over, right? And so there are several efforts being applied to that. We're trying to basically train an agent to just learn some part of the of how the simulation should what, you know, what the physical data the simulation should provide. And so I've worked on some of those things. There's more of that going on. Yeah, so there's more details to that as well. I mean, the way we do our simulations, right? We divide, you know, you can sort of think of our simulations, our multi-physics simulations, like, you know, like an image, right? An image divides to make an image, you divide it up into a whole bunch of little tiny pixels, right? And each pixel has a red, green, blue value, and that's what makes your image. And we kind of do that with our simulations. If you want to simulate a whole room with a capsule inside, you basically divide it up into a whole bunch of little tiny pixels, but we call them nodes, and we interconnect them with their nearest neighbors. So they create that links into a mesh. And rather than having red, green, blue, we have physics attributes. We tell it what it's made of. That node is what it's made of, how hot it is, you know, things like that. Its ionization state. And then we run the laws of physics on all of these nodes as they talk to each other, and then that unfolds. And so, but as you can imagine, if you have sort of a mesh of all these nodes, they can tangle up and they can get all messed up. And so one of the things that we do is we have, you know, a certain amount of algorithms to try to keep that tangling from happening too much and crashing simulations. So that's sort of an inside baseball thing, but that's one of the things that I'm one of side projects I have, for instance, of actually using reinforcement learning to try to figure out, just by giving it a whole bunch of trials, what's the best policy for relaxing these nodes so that they don't crash a simulation. Yeah, and these things these things just make simulations easier again, right? And all of this, so you can ask questions and explore more quickly and easily.
Right. We all know how tricky even 3-body problems are in an orbiting system, where they can become chaotic. And well, imagine this thing you're describing, is the interactions are insane, right? And so if you could get something to predict, you just say, here's a million different examples of what happened, how it started, and how it started, how's it going, sort of examples.
Right, exactly.
You got it. It started, we're thinking here, how's it going to go, right?
Right. And of course, that's an experience in itself, right? I mean, to actually take these forays into data science and large scale data sets, and training in multiple GPUs and stuff like that. It's been fun. I mean, I know people do that all the time, but it's interesting to have that experience.
Yeah, for sure. There are some interesting articles of actually the CogSim team at LLNL and some of the work being done there. So I'll link to those articles in the show notes. People can check that out. Now,
exactly.
One final thing. Yeah, go ahead.
Oh, no, just basically what you said. That is the team I'm kind of referring to, that there is this effort to bring machine learning to bear on some of these problems. And so that's good work that they're doing.
Yeah, of course. We're getting short on time here, but let's wrap this up with one other aspect. You talked about having air-gapped systems, and not everything necessarily should be online or is online. You want it to be all kind of isolated and stable. So, and then you've got a lot of computation you got to be doing. Tell us just a bit about the computing environment. You have like interesting clusters or grid computing, or what's the story for actually running all this stuff?
Yeah, good question. Yeah, there's for the context. So basically, we have a bunch of very, very large computer clusters at the lab, and some of them, are like near the biggest computers in the world, or were at one time and such. I don't keep track of that, but those are all on lists, and there are new ones on the horizon that will take that crown again. So what we do is basically submit our jobs, carving out some chunk of the machine, to run these multi-physics simulations for so many hours or days. And so we're doing that. We do a certain amount of that on the open side, but then we have a lot of resources on these air-gapped systems, and so we do a lot of our running there. And so that's sort of the exigency of moving our data, physical data from the NIF, and our tools over there. So we always have up-to-date tools to run there. And so, yeah, we have, and these are made by different vendors, and it's interesting. They're evolving where there's larger GPU components than there used to be, and the codes are learning to adapt to that. So it's a fairly dynamic environment. And so that's kind of I guess the general run environment we have, that we're running on a bunch of clusters.
How's quantum computing looking? Are there any quantum applicable problems here?
Not directly, from my experience. I know there are some people working on quantum computing at the lab, but I'm not closely attached to that. So
I'm specifically thinking, like, if you had a quantum computer, would this allow you, not necessarily like trying to invent quantum computing, but somebody
probably not. I mean, I maybe somebody else would know something, but yeah, I mean, really, we're just trying to kind of integrate these differential equations that describe the physical system, and sort of maybe there's a way to diagonalize a matrix with quantum computing that's way better than than an explicit method that we use. But yeah, I'm not aware of it. So
Yeah.
at this point,
I definitely don't know enough about quantum computing to even suggest if I have an opinion on this, but
well, I guess we're due now if these barriers are falling, right? ChatGPT.
that's right. Where's the
and
trifecta? Come on.
yeah, exactly.
Get
We
it?
have a triumvirate of new things. Be careful
Absolutely.
what you wish for, though, right? I mean, having be able to crack any password, I don't know if that's a good thing.
Exactly. I'd love faster computers. Wait, baking doesn't work anymore. Oh no.
Right.
Back to rubbing sticks together and sleeping on the wood. I don't like it.
Exactly. I've got my money clip that I keep everything on my person.
Exactly. I'll mail you some cash in physical mail. Get this app.
Right,
Yeah,
right.
so you're right. Careful what we wish for. And we won't have that much cash because ChatGPT will be writing our software that we used to write. So it'll be tough.
Well, this is true. This is true.
No, honestly, I'm very optimistic about the future and a lot of these things, and especially this. So awesome work. Now, before you get out of here, let me ask you the final two questions. If you're going to work on some of these Python projects, what editor are you using?
Yeah, so I've kind of gone through the litany of editors in my evolution. I started with VI and went to Emacs, used Emacs for a very long time, and then probably 5 or so years ago, I decided I need to make a change, and I went to Atom, and I could use Emacs binding, so I didn't have to rewire my muscle memory. And really enjoyed that until, of course, last summer when they killed it, and so I had to look around. And it was funny because I had a summer student who I had just told how to use Atom, and I was like, "Oh, this is great!" And then I had to tell him, like, literally a week later, "Forget that."
That thing you really love, they canceled it. I'm sorry.
Yeah, just don't. He was like, he liked it too. But so I looked around, and I think I did what a lot of people are doing. I went with VS Code, and I love it. My goodness, it's really mature and good. And Copilot, it's again, it's I'm still learning how to use it effectively, but it's amazing. It's a state changer.
It is absolutely amazing.
Yeah,
I feel
and the
like
fact that you can. Oh, sorry. Just because we are working on clusters, a lot of things are remote. The fact that you can do remote SSH, and you can have your software here and your notebook here, and then a terminal below it, and it's all just in your VS Code window. It's pretty sweet.
Yeah. You kind of connect to it, have your editor running locally, but connected to that
right
there. Yeah.
There's no delay with typing and all, but you are running on the heavy iron somewhere, the big iron somewhere.
Indeed. I feel like VS Code is maybe the natural successor to people who did Sublime and Atom. Those are the, I see that kind of that flow there. All right, and then notable PyPI package.
So, well, right off the bat, you put up at the beginning, llnl.github.io is I think a really good resource for just sort of seeing the open source packages that are being developed at the lab. And again, they have a bent towards high performance computing and such. But like I said, eventually iDesign will be up there. We'll open source that. I will mention one that Dave Monroe, again, in his sort of trying to take care of us before he retired. He wrote a nice little package called QND, which is on this for quick and dirty QND, and that's now being maintained by Dave Strozzi, and it's a nice little package, but what it does is actually unifies an interface for several different binary formats, in particular HDF5 and netcdf and a lab internal format called PDB. And it's one of those things that passes the test in my mind, where I've actually reached for it in my own just little projects, where if I need to just store some data, right? NumPy has its own storage things, but it doesn't do really good if you have a hierarchical data, or if you want to do records, and have things, stored over time. But this is actually a simple enough and uniform enough interface that it's like, wow, this really works. And so anytime you actually reach for it when you just need that tool, I think that, it's past sort of some sort of threshold of usability. And again, it's
Yeah.
open source, and I think for people who do things like that, work with binary data, I think this might be something that other people might want to look at.
One of those Lego building blocks.
Yeah, exactly.
One other question, people out there who are really interested in what you're talking about, and maybe they previously thought of LLNL as just a place for physicists, and maybe you're starting to think, oh, maybe it's a place for software people and data scientists. Are
It
you guys
certainly is,
hiring?
actually.
Is
We
there a
are
lot of
actually.
opportunity for folks?
Absolutely, actually, right now, strangely, I think there might be some tailwinds after this success. I mean, that's above my pay grade, but I think that there's that's something that should be happening. There should be a lot more good stuff going on. But right now, even there's a lot of hiring going on, and so if you find some of this interesting, and you have Python chops, check us out. Definitely.
Awesome. Jay, thanks for being here. Congratulations once again. It's really amazing work, and I know it's early days, but we'll look back on it, I'm sure.
Yeah, thank you, Michael. Yeah, it's been a lot of fun. It's fun to be a part of it and look back on the road. And as you say, it's still a long road ahead.
It is, but I'll be tracking it. It'll be exciting to see where it goes.